Hello, my dear friends. Today we're going to talk about the portfolio optimization, and we'll briefly describe the idea of Harry Markowitz, which was developed in the middle of the 20th century. And he received a Nobel Prize for this problem, for this study, but a little bit later. So, suppose we are interested in investment in some number of, let's say, goods or shares or stocks or something which is valuable to invest. And let's say we have n shares, n kind of shares. Let's say first, second, third, and etc. and then. But we have only a limited amount of money, usually, right? So suppose we've invested W1 part of our money to the first share, W2 to the second, and etc. and Wn share at the end. Typically, like this whole sum should be equal to 1, because each W is a part of our investment, which means that, let's say, for a very specific example, suppose we are interested in like Apple investment, Facebook or Meta, and Bitcoin, BTC. So we will have three numbers. Say I would invest half of my portfolio in the Bitcoin, like 20% to the Facebook, and the rest, which is 30%, to the Apple company. Typically, all these numbers are greater than 0, greater or equal than 0, but we'll consider the cases when the number could be negative. And this vector of n numbers, 3 in our example, we'll call this portfolio allocation vector. So this vector will be from n-dimensional Euclidean space. And as I said before, it is easy to think about it as a vector of non-negative entries, but still there is a situation when the entry could be negative. We'll consider it right now. Generally, there are only two options on the market when you invest in some share for a short time. The price could increase, or the price could go down, like here, let's say this price and this price. The graphs, the actual graphs are typically quite sharper and less predictable than this, but let's consider this for simplicity. This is graph of price from time, let's say. And when you believe, then the share will go up to the moon, right? We just buy at the beginning some share, let's say for $100, and later, so here we buy, here we sell. Very easy strategy. Here the price is $300 and profit. But what do we have to do if we believe that the price should go down or decrease? Then, in this case, like suppose the initial price of a share is $300, and you believe that this share will go down to $100. And in this case, you actually not buy a share, but you can borrow a share from a broker. Here you borrow one share, but you have to return the share a little bit later. For sure, with some commission. That's how the broker earn their money, but still we can borrow this share, and at this exact time we are selling it instead of buying as a previous example, and we have $300 here. But later we buy again this share in order to return it to the broker, right? So here we return the share and we have our $200 left. That's our profit. This, like the first kind of positions, is called long positions, but the second is called short positions. Because typically you could borrow a share only for a short period of time. That's why it's short. And it is easy to think of a long position, as a positive one, because we owe some share of a company, right? Some papers, some rights, and etc. So it doesn't matter for us. Some valuable asset. But here, when we have a short position, we actually have to return this share, which means that we own negative amount of shares, right? Because when you owe to someone like $100, you have to it's pretty the same that you have minus $100 on your balance, right? Okay, great. So we've talked about short and long positions and the difference between them in terms of entries of our portfolio allocation vector. And again, our constraint here is typically written in this way. And when your portfolio is long only, which means that you do not borrow any shares from the broker, it's pretty reasonable to have this requirement, because it literally means that all your investments sums to 1, because they all are a part of your big case with the money. Okay, but even if you have some short positions, that's still the restriction here. So suppose we have some position which contains short positions. Again, let's say we have this vector 0, 5, 0, 2, minus 0, 1, and let's say to sum it all to 1, we have to put here this, right? So we have this position. And actually, if you calculate the one norm of a portfolio allocation vector, we'll obtain an amount which is called a leverage. Why so? Let's calculate it. So suppose we have this vector W, and in this case, this vector W, when you calculate a one norm here, and I remember you that one norm is just a sum of all absolute values of all entries. It is nothing else but 0.5 plus 0.2 plus 0.1 plus 0.4, and you can see easily that this thing is greater than 1. Moreover, it is equal to right? And actually, this leverage shows you the amount of money which is stolen from broker, like which you borrow from broker, because when you have long only portfolio here, for sure the sum of all positive entries will coincide with the sum of their modulus, which means that if you consider long only portfolio without this minus here, but here should be a little bit less, for long only portfolio, this leverage will also be equal strictly 1. But if this one norm is greater than 1, that clearly indicates that you borrowed something from broker. That's not a crime, but still you have to like separate these two cases. And the more your leverage is, the more shares were stolen, were borrowed from broker, the more you own for broker. Okay, let's go further. Let's go. Suppose we have some history of prices, let's say. Let me write an example somewhere here. Suppose we have a history of prices. Let's say this Tesla share prices. Okay, suppose the graph is something like this, I don't know. Which means actually that each day, typically each day, but actually pretty each second, you have a number which indicates the market price of a share of some asset here. So you have this data like price and some timestamp. And let's say you're like following the prices once per day. That's not necessarily the case, but that's one of the options. Let's say, I don't know, 101, first day, second day, third day, fourth day, fifth day, etc. 109, 200s accidentally, bumping down, 80, and let's say 105. Okay. Typically, this information could be obtained using some libraries like Yahoo Finance, and we'll show you how to use it. And at the end of the period, and typically we are considering this day period, we have the final price, right? And we can calculate fractional return value, which is nothing else but this fraction of difference in price related to the initial price, which literally means the following. I can calculate fractional return here, fractional return per each day, right? Which means that again, I have this 1, 2, 3, 4, 5, and here, like at the end, I have 0, let's say, but then I have 100.9 minus 100.1 divided by the initial price, which means actually something like 0. Let's say 0, and one more 0, right? No, 0, 0, 8. That's this value. Next day, we have something like doubling our price, which means that the difference of the same magnitude as initial price, and the fractional return in this case will be something like 1, which is great. Like if it's not a Bitcoin, that probably will never happen, but still. Next day, the price decreases, which means that your fractional return will be negative. And the formula for it is 80 minus 200 divided by 200, which means something like okay, this, right? Minus 60% actually, minus 0.6. And again, you calculate this fractional return as 105 minus 80 divided by 80. Okay, I don't want to calculate it, but hope like you got the idea here. And each of your asset has its own fractional return history. And on average, each day you have, let's say here again, for each asset I have this fractional return per each day again. And if you weight it with your portfolio allocation vector, you'll receive your average portfolio return. Again, suppose you have this data for, let's say, for Tesla, right? Which means that for Tesla, you have this history of fractional returns. For, let's say, Apple, for Bitcoin, and etc., you have a history of these fractional returns here. Again, some plus 0.1, minus 1, plus 2, I don't know, minus this, and etc. and etc. And each day you can average it using your weights of your portfolio. Let's say here is minus this, and here's plus this, and etc. So if you will just multiply each this fractional return by your portfolio weights, you'll get this W transpose R, which is your portfolio return at this day. Portfolio return. That's the scalar, and that's the price which you have like at the end of the day. At the end of the day, your portfolio in average or in general increased or decreased by this value. All right. Next day the same, next day the same, and so on. So that's about return. But we also, we have a history of this fractional return, as I said, and average value during the period, let's say a year, of these returns day by day could be averaged, and you'll receive a mean value, which is a characteristic of each asset here. And here you can have this vector mu, and let's say we have say n assets, which means that mu is n-dimensional Euclidean space. But again, how to calculate mu? You have to go through all your data per each asset, again, and calculate an average value for each asset, and that will be mu first, for example. Average value of fractional return for the second asset will be mu second, and etc. and etc. and etc. You'll obtain mu vector at the end of this calculation based on historical data. But what about the variance of such approach? Could you somehow calculate the measure of how these assets or shares are correlated with each other? And we have this option, and this option is called covariance matrix. And you could construct it because, again, you have this R vector evolution. You have this static mu vector which was calculated before, and you can just subtract mu vector from each of a column of your history data previously and calculate this matrix sigma. That will be your variance or covariance matrix here. And interesting thing here is that this covariance matrix actually indicates the risk of your return, or the dispersion, right? The variance, because the more the variance, the higher you have a chances to receive less or high at the same time, right? You have some uncertainty when you increase a variance. And the variance could be calculated for your specific portfolio. Because, for example, if you investing only in like some sector, let's say IT sector, and probably a lot of shares here are correlated somehow because, for example, I don't know, here we have .com bubble or some other, I don't know, development companies bubble and etc. And like imagine that all prices will immediately go down, breaking and etc. And if all of your investments are in the one sector, for example, let's say IT as I said, or development or something like this, probably you'll lose a lot. But to model it, we'll consider this variance, which is calculated for your specific portfolio. Sorry. And note that this variance is a scalar here, while the covariance matrix is a matrix, unexpectedly. Okay. And typically, what was the Markowitz approach here is that we want to maximize our return. That's the return. At the same time, we want to minimize our risk. That's why we put this risk with a minus sign here, with a negative sign. But actually we have this gamma scalar here, and this gamma is just some risk aversion parameter, which means that the higher the gamma, the more important decreasing risk becomes to you. The lower the gamma, the more you are focused on increasing your return. But high return typically coincides with high risk. You cannot give both simultaneously, high risk and low return, right? That's reasonable. So this is a risk aversion parameter here. And here we can formulate an optimization problem. And we have some questions about this problem. How hard is it to solve this problem? Is it convex problem or not? And we can easily answer some of these questions. First, about convexity. This is the problem, and W is a variable here. We'll start with the budget set here, and we'll start with the constraints. And in this problem, the only constraint that we have is that 1 times W should be equal to Y. And this is actually a convex set, because this set is actually just a plane, right? Or it's pretty easy to verify that this is a convex set, because this constraint is affine or linear constraint, and we know that when we have linear equality constraints, the budget set is convex. What about the function here? And like, to give a fast answer, so a quick answer, we can just think of W as a scalar. And if W is a scalar, that's just a quadratic function with a negative sign before the squared variable. For example, let's say mu W minus gamma W, gamma sigma W squared. If gamma is a scalar, if W is a scalar, sigma is also a scalar. And that's just this parabola. And is this function convex? Actually, no, but this function is concave, and we have a maximization problem instead of minimization, and we can convert it to minimization problem. For example, if we minimize the negative of our objective function, which is minimize the risk minus return. That's pretty the same, exactly the same problem. And in this case, we have this function, which is a convex one now. That's why the problem is convex. And that's great news for us, because even in vector case, the problem is still convex, because matrix sigma should be symmetric positive definite matrix, because it's a covariant matrix by construction. Okay, so we have the problem. We know that the problem is convex. How do we solve it? The simplest way is probably solve it with CVXPy library. Let's consider some examples of using this approach. Firstly, we generate the matrix sigma on artificial data. We also can try this approach on a real data, and you have such an exercise in your homework. But here we generate this sigma matrix artificially. So what do we have to have? We need to have sigma matrix and mu vector here. That's mu vector here. And why do I multiply sigma matrix to itself? Because I need this matrix to be symmetric positive definite. So firstly, I generate a random matrix, then I multiply it by itself, ensuring that it's SPD. Next, I'll formulate a problem here. So our W is our portfolio vector, which we are seeking of. The gamma will be the parameter here, because we can turn this risk return trade-off by tuning our gamma, which means that the higher gamma means that we are not tolerating, we are not so tolerated to the risk. The lower gamma means that, okay, we can risk. Here we formulate our objective function. It's just mu transpose multiplied by vector w, or otherwise, or vice versa. It doesn't matter here. We formulate a risk function as a quadratic form based on matrix sigma and vector w, and we formulate a problem of minimization of gamma multiplied by risk minus return. We could easily switch it to maximization problem without any loss of generality, because that's exactly the same problem as we discussed before. But here we'll consider long-only portfolio because we explicitly state that all W's should be non-negative. Okay, what do we do now? Now we sequencing over different gamma values from 10 to the power of minus 2 to the 10 to the power of 3, which means that super highly risky strategy, and this is a super conservative strategy. And we are enumerating through this array and solve each problem. So we set the value of gamma and then we solve a problem. Okay, let's go. And here we receive this picture. And what's the point here? What are the points here and what's the idea? These points, actually red points, are indicating the exact solution in case your investment, all you have in only one single asset, only one single share here. So we generated the problem with dimension of 10. So each of this red circle means just what would be if I'll take all my money, all the money I have to one asset. For example, the first asset, the second, third, fourth, and etc. I don't know the exact numeration here, doesn't matter. 10. Let's say 5, 6, 7, 8, 9, 10. Yes, and that's it. But what is this? This green curve is actually a set of optimal solutions for different values of gamma. That's the most interesting part here, which means that we have this transition from lower to higher values of gamma, and the lower values of gamma, as we said, means good tolerance to the risk, which means that here we are risky guys, here we are conservative guys, which means that we do not want to risk. And let's take a closer look here. Again, what do we have? For example, in a risky strategy, and we see that here we have a point which lies on this green curve, which means that probably this asset was the most profitable one. But the most profitable one asset like ensures the high risk, right? Because you didn't know it in advance. And actually the whole idea of investment according to Markowitz portfolio approach, based on the idea that you can estimate historical data and make a decision based on that, but we know that on real market we cannot do it actually, right? Because you do not know exactly what will happen. And yes, that's it. What's interesting here that if we would invest all our money in this first asset, we'll receive a maximum value of return here, maximum return value. At the same time, we'll have very, very risky strategy here, right? That was very risky. But you know, all other points are worse than the first one, because if you invest all your money in some strange asset, not the most profitable one, you will have high risk and low return at the same time, which is bad. That's why we are interested in building some optimal portfolio in some sense, right? Okay. Let's take a look at the plot of how your return is distributed with different values of gamma. And as we said, the lower the gamma, the more tolerant to the risk you are. Here is the blue line here. Oh, am I right or not? Yes. Let's take a look. Yeah. Let's say blue line means that in average, you will get more than in this orange approach, right? But you also have a higher chance of having lower than in orange approach with higher value of gamma. Okay, so this is inverted proportional to the value of mu, right? That's pretty reasonable. Suppose we now allow our portfolio to be not only containing long positions, but the short positions as well, and we'll make some assumptions on leverage, such as a leverage limit, for example. And typically, you cannot borrow a lot from your broker, and these limits are set up by your broker. So you like typically we have this constraint here by law. Okay, we said that L max is a parameter here. We formulate a problem where the one norm of our portfolio allocation vector could not be higher than this leverage limit. Then we'll go through different leverage limits. For example, leverage limit equal to 1 is strictly forbidden for short positions, right? The short positions are forbidden when L equals to 1, but when L equals to 2, approximately half of your investment could be borrowed from a broker, and etc. So the more leverage means probably higher risk, and we'll take a look at the real world simulation. Yeah, that's it. That's pretty it, because let's say here is long only portfolio. This is long only portfolio. And for like with increasing of your leverage limit, here is L equals to 2, here is L equals to 4. You're increasing both risk and return. And that's usual, that's like classical situation here. So here you can gain more in terms of return, but at the same time you have bigger standard deviation, and at the same time the same conclusion for bigger value of L. Okay. That's, for example, the graph of the component of investment per each asset. We have only 10 assets here, and let me take a closer look. Here are the colors here are coincide. Yes, Not really, I suppose. But I think that the red means here uh, for L equals to 4. Let's verify it. BGR. Yeah. So the blue for long only, and the green, yes, that's it, for middle case. And there are third, like, variants of investment. For example, you can invest almost all that you have in this asset. At the same time, you borrowed this, and you borrow this, because you believe that these shares will go down, and you invest in short position here. And you have a higher return with a higher risk at the same time. And a lot of variations could be added here, even in a framework of convex optimization. But for example, you can include any commissions of a broker here. You can include, let's say, the minimum value of return if you want to receive a portfolio which is profitable, which should be profitable than some minimum level, or some like other modifications that are available here. And one more interesting approach is when you're dealing with a very large number of assets, let's say not 10 as it was discussed before, but I don't know, thousands or dozen of thousands, or like million assets. Okay, million probably too much, but let's say 10,000 assets. In this case, it's pretty hard to solve this problem, and you'll wait a lot for solving it. And if, for example, you are a high frequency trader which uses who are using Markowitz portfolio theory, which is actually most probably not the case, but still, you have to solve this problem quickly. And we have one approach to solve it, like to deal with it, that's called factor covariance model, which means that imagine that we have a list of shares, I don't know, 10,000 shares, but a lot of them are correlated with each other, and you believe that you have some, let's say, sectors of economy, and let's say this is IT assets, this is, I don't know, oil and gas assets, this is cryptocurrency assets, and etc. And you are defining how much each of these 10,000 assets is loaded to some sector, some factor. Sector is the term from the economics, and the factor is from mathematics here. And you actually factor your covariance matrix because it's too big to store and to operate with. And imagine that, again, n is equal to 10,000, and k as a number of factors, let's say, I don't know, 10 to 100, something like this. Then you form this idea, n times n, what's your covariance matrix, but factorization of this matrix is following: n times k multiplied by k times k multiplied by k times n plus, optionally, n times n diagonal matrix D of what is called idiosyncratic risk, which means that the risk related to individual assets, related to individual assets, because even a lot of assets are connected with each other during this factors or sectors, typically still like some individual behavior could be catched using this degree of freedom in our model. We have this additional plus d, which is optional, but still this diagonal matrix. If the d is a dense matrix, we would not win anything in this case. That's why d should be diagonal. Okay, and what's interesting here is the risk before this factorization was following, but now the risk is W transpose multiplied by F multiplied by a sigma with a wave multiplied by F transpose W, which means that F transpose W is a k-dimensional vector, which means your like investment vector in different sectors, not an individual asset. And actually, literally, ij element of this matrix, meaning exactly loading of asset I to a factor j. That's how it constructs. For example, you know that Facebook is mostly in IT sector, and that's why, for example, if I have asset Y, which is Facebook, and you will have this row here, and this will be almost zero everywhere except IT and probably I don't know, advertisement sector. It doesn't matter. So you construct this matrix F, and in this case you have to carry out less calculations than it was before, because you just downscale the like total dimension of your problem. And sigma with wave is now a covariance covariance matrix between sectors, not between individual assets. And like, what's the profit of this formulation is, before this your complexity was O from n cube operations, but now you have O from n times k squared operation, and if k is way more less than n, you will win a lot here. And in the particular example here that was carried out on MacBook Air, but old MacBook Air, but still, you'll have this number of seconds for the factor model and this for the full model, which was not modeled in a factor way. The overall results actually will be pretty close to each other, but still the results, like the difference in time, sometimes worth the the efforts. That's it for today. Actually, we have some materials and links, and this Colab notebook is available on CVXPy examples page, which I strongly recommend to investigate. Thank you.